Hello and welcome to lesson 4 of week 12. In this lesson, we are going to build a real-world app to illustrate the graph data structure. My name is Mildred. Now we have a scenario where we want to build a package delivery routing system. Now let's say a company that manages package drop-off between warehouses, and let's say the warehouses are named A, B, C, and D and E. Let's have 5 warehouses. We'll name them A, B, C, D, and E. All these routes, they have travel times, and these travel times are the weight. And we want to build a system that will store the weighted graph that will allow breadth first and depth first search like this, like we've created, to allow this navigation through it. It's like the traversal, and then that will be able to compute the fastest route from warehouse A to every other warehouse, and we'll be able to perform topological sorting, planned build order. So if the graph is a DAG, we want to do the topological sorting. So now let's say they gave us a table of the weights and say from A to B we have the time in minutes to be 4. Let's illustrate this. Let's say warehouse. So let's say we have this scenario where we have from A to B we have 4 minutes to get there. Now we have another scenario A to C and we have this to be 2 minutes. Let's say we have B to C, B to C, and B to C is 5 minutes. Let's say we have B to D to be 10 minutes, right? Then we have C to E to be 3 minutes, and E to D to be 4 minutes, and D to E to be 1 minute. Let's say we have this table of the weights, which are the time in minutes, right? So these are different warehouses. You can give them any name you want. I just use A to E. Now the algorithm we want to create for this solution is to create a graph class that will store the weight route or the weighted route, and we want to use adjacency list like we have done previously. We want to add the edge. We want to perform breadth first search from the start to any warehouse, depth first search also from the search path to any warehouse. We also want to implement the Dijkstra's algorithm to find the shortest travel time from warehouse A to all other warehouses. We want to implement topological sort only if there are no circles, so we'll check for circle first and then we'll print the readable route and the distances. We can also go advanced to display the final shortest route from maybe warehouse A to warehouse D, and we can check if the graph is a directed acyclic graph in our solution. So like always, we're going to use the heapq module, so we'll import heapq. Then we'll use the deque. So let's say from collections we want to import. Now let's create the graph class. So say class graph def init self.graph is equal to that. Now we want to add edges here to the graph. We can create the add vertices method where we add vertices to the graph, but what we are required to do is to store the weighted graph. We are to allow the traversal, which is going to be navigation. We want to use both methods that we have learned so far. We want to compute the fastest route from warehouse A to all other warehouses, and we can decide to get the route to a particular warehouse also, and we want to check if it is a DAG. Then we want to see if we can perform topological sort there also. So let's say we want to add an edge to this weighted graph. So let's do the add edge. Now there are many ways you can do this. You can think about your algorithm as long as you get the solution. So we'll put self vertex 1, vertex 2, and then the weight. Okay, so when we add A and B, we know that the weight is 4. So now we want to say if U, not vertex 1, not in the graph already. So if it's not in the graph, we want to say self.graph U will now be equal to, we'll have an empty list. So we're going to be storing this as the key, and then the value is an empty list, and we'll put the adjacent vertices there. Now we can now hand V and the weight. Now we are looking at this as a directed graph, right? We're not having the two conditions that we did like in the last lesson where we checked if directed, set directed to false or true. So let's just do this simply and say self.graph u.append. So now I want to append V and the weight, right? So you can actually add a directed parameter here and set it to false, and now check if directed there, and then you will add a condition if directed, and then you add a condition if not direct. So by default everything will be false, so we don't have a directed here. It means that it's not a directed graph, and maybe it's an undirected, and so like we did previously where you say if not directed. So let's do the breadth first traversal, and then we'll do the depth first traversal, and then we'll we'll do the Dijkstra algorithm to get the shortest path. We'll do the Hans algorithm to do topological sort, and then we are going to have a driver code that will run. So now we've done this, and let's say def. I'm going to just go ahead to write this since we have done the same thing in the previous lesson. It's just the same implementation based on the requirements that we have. So I'll do start. I'm going to come here and just copy this that we did previously, so I don't have to spend time typing all of that. I will try to do that for this. We might have to change it a little, but let me copy this first, and then we'll do a little changes, and then we'll do the Dijkstra, and then we can do the topological sort where we use Hans algorithm. Let's copy this. So we'll copy this and I'll explain while I edit it. So now let's go back to what we've copied. For the breadth first traversal, we created the visited variable, and we want to have an empty set where we store all of the visited nodes. We have this order here where we want to use to check when we have all the nodes in the order. Now we have the queue where we pass in the start to the dequeue method. So while queue, we want to pop left. So for queue is first in, first out, and then we'll store that in node. And if the node is not in the visited already, we want to add it to the visited and also append it to the order list here. Now we can loop through the graph again to be able to see the adjacent vertices. So we'll say for neighbor in self.graph node. Now we want to change this because what we are trying to do here is to get all of those nodes, and we'll get like an empty list of adjacent vertices or things like that. So we'll say for neighbor underscore, just a throwaway variable. You can use I or whatever you want. In self.graph, let's use .get, and we want to get the node and empty list, right? So we get this like that. So if the neighbor is not in visited, we'll append to the queue the neighbor, and then we return the result. Now for the depth first search, we do the same thing, and we have an outer method and an inner method. And what we are doing here, we can actually change this to do something else where we just have a helper method where we say we do all of this in a helper method, and then let me do that so that you can have a different way of doing this, so you're not stuck to just one method. So we have the self start, we have visited, we have the order, and then here we can now say self dot. So we'll create a helper method and we'll call this TFS helper. We'll pass in start, we'll pass in the visited, and then we'll pass in the order, right? So here we'll create the helper method. Let's call this helper, and this is not going to be an inner function anymore. So we'll have DFS helper, we pass in self, the node, the visited, and the results. Okay? So let's delete all of this down. So in this helper here, we want to say if node not in visited, we want to say visited dot add the node, and then order dot append node. So you see it's similar to what we have done before, but we just separated it into two different methods. So I can say here for neighbor in self dot graph dot get node an empty list self dot underscore DFS helper neighbor visited results. Okay, so we have this implemented like this, and then we can use this helper here. So I just separated them into two different methods. For the Dijkstra algorithm, we use this to get the shortest path. It's similar, it's still the same thing, and we just copied what we have done previously here. Here we can actually check for infinity somewhere else. So let's say continue here, and then for neighbor wait in self.graph, let's get the current node. So we have the current distance here. Let's get a current node, this node here. So let's say dot get. All right, so we want to get the node and an empty list like this. So let's make it uniform there. Distance is equal to current distance plus the weight, and if the distance is less than distances, let's use dot get. We want to get the neighbor, so distances dot get. Let's say we're getting neighbor loads. I think this should work. Distances neighbor is equal to the new distance, and we push this to the priority queue. New distance neighbor, we return the distances. I think this will work. And then for the topological sort here, we set in degree. Let's set this to just an empty dictionary, and then we say for node in self.graph, let's say in degree node is equal to 0. Let's change this to be like this: in degree node is equal to 0. And then let's say for I'll say for node in self.graph. So you can see we're doing this in different ways. So we have this one, so it will be the same. So for node in self.graph, we want to now put this for neighbor underscore in self.graph node. If neighbor is not in degree here, enable this. Let's say if neighbor not in degree, then we'll say in degree plus equal 1 go to the queue node for node in self.graph. If in degree node is equal to 0 here, and then the order, topological order here, while queue will pop left, we will append then for neighbor in this. So for neighbor in self.graph, have dot get node and an empty list, I think like this. In degree neighbor minus equal 1. If in degree neighbor is equal to 0, we append to the queue. And then if length of the topological order is not equal to the length of, let's say it's not equal to the length of in degree. So if this is not equal to the length of in degree, we want to return circle detected. We can raise exception, we can return circle detected. Let's just return here. Let's test this before we end this lesson, and let's see if this actually works, because we didn't test all of the ones we created in last lesson. So let's see this that we're doing. We're trying to get a warehouse distance, or we're getting shortest path from one warehouse to all other warehouses, and for this scenario we're trying to get from warehouse A to all other warehouses. And then while doing that, we want to be able to iterate. We're able to get the shortest distance, and we created methods that we can use to return the distance of all other warehouse from A, the shortest distance, shortest path we can calculate. Then we can also calculate, so we'll do from A to A, from A to B, from A to C, from A to E, from A to D. And then we have the shortest time that we can compute from, let's say we want to do from A to a particular warehouse, and then we want to try to do the topological sort and see if there's a circle detected. It's not possible. If there is no circle, then we want to do the sort and return of value. So let's do this. Let's say if name, so now we want to say g dot add edge, and we're adding a b. So let's a b. So we have the weight that we wanted to add here. The distance from A to B is 4, so just add that a b for the weight for the time. So we'll add this up until all of the what we have on the table. So we have A to B is 4, we have A to C is 2 minutes, right? Then we have B to C, and we have B to C to be 5, 10, 3. So we have B to C to be 5 minutes, B to D to be 10, then we have C to E to be 3, then E to D 4, D to E 1. So here we have E to D 4, and then D to E we have 1. So we have all of these edges added. Let's print. Let me start a new line and say breadth first search from A, and here we'll do G dot BFS and also apply the start, which is A. We'll do depth first search, and we'll do this from A. We'll change this to TFS A. We want to have the shortest path from A. Let's use this Dijkstra algorithm here. So we'll say Dijkstra. So when we get this shortest path from A, let me print this like this. So the shortest path from A, then I'm going to say the distances is equal to G dot Dijkstra, and I'm doing this from A, right? And for node and distance, in distances items, and I want to print. So I want to print the key and then the value, right? So we'll have print A. Let's put an arrow. Let's print the node and the distance. Let's put a space. So let's say node and distance minutes. So we'll just print it in formatted form, and then let's put the shortest path here. Print shortest time A. Let's say we want to have from A to, let's have a shortcut from A to D. So this is equal to distances D. And let's say minutes. Okay. So we have this well formatted text that we want to try to use and see if this works as we want it to. Let me put a backslash n here. I'll remove this format string. Now let's do a logical sort. Let me print backslash n topological sort. We'll put g dot, and what's the name of this? Sort can. So let's run this and see. We have g is not defined here because I did not instantiate the class. So we'll put g is equal to right. I'll run again. We have for name underscore in this on line 30 in BFS built-in function or method. Object is not subscriptable. So let's look at it on line 30. So these are all problems with copy and paste. So it's not subscriptable. We're supposed to put this not a list, right? And I'll run again. And name order is not defined. Order.node line 44. This is the copy and paste issue also. So we have order.append node name error, and here I do not define order. Okay? And so when I clear here, I will run, and I have name result is not defined here because I use result instead of order. Okay? So I'll run this again, and then we have it working. So you see all the copy and paste issues I had. So we have the reference search from A. We have all of the accessible warehouse A, B, C, D, and E. We have depth first search from A to be none, which is not correct because something must be wrong here. Okay, we didn't return anything, so it's none. So let's return. So I think that is the problem. So let's clear this and we run this. Okay, so now we have the depth first search from A. We have A, B, C, E, D, which is what I expected. The shortest path from A to A 0 minutes. We're already in warehouse A to B 4 minutes. We have A to B 4 minutes. When we have A to C is 2 minutes because from A to C here we have 2 minutes. So we have from A to A 0, A to B 4, A to C 2, A to E 5, A to D 9. So we have from A to B. So we're looking for the shortest path because there are many paths to get to D from A. So we can go from A to B, which is 4 minutes, right? So it's going to be 4 minutes plus from B to D 10 minutes. So this will be equal to 14 minutes. Which other parts do we get from A to D? So if we get from A to C, it will be 2 minutes plus look for C to D. So from C, we don't get to D, so we don't have a part from there. So we have from A to B 4 minutes, from B to C 5 minutes, from C to D. So we have to go to E, then E to D. So we have plus 3 plus 4. So this will take 8 plus 5, 16. So this will take 16 minutes. So we want to look for another part that we can get to D, that is the shortest part. So we can say from A we want to get to B, which is 4. From B we want to get to D, 14. We've already done that. From A we want to get to C, 2. From C we want to get to E, which is 3. So we'll say 2 plus 3. From E we want to get to D, which is 4 plus 4. So this will be 9. So from what we've done now, the shortest part is 9 here. So this is like the shortest part problem. You can manually try to calculate all of this to see. So our algorithm works well. And so the shortest time from A to D will give us equal to 9 minutes here. And so the topological sort will have A, B, C, D, A, B, C, E, D. So go from A to B to C to E before you get to D. So this is the topological sort. And when we do all of this, we know that there's a circle detected. So in our live web conference, we'll try to do another app example, and we'll have detailed and more understandable explanation of all of what we have done in week 12. Thank you, and see you next week.